Hello everyone. Let's start with something simple. Have you ever opened a packet of chips while traveling in the mountains? The bag is all puffed up, right? That's because gases behave differently when pressure and temperature change together. Now, we already know Boyle's law and Charles' law, which separately deal with pressure and temperature effects. But in real life, gases rarely give us that luxury of keeping one factor fixed. So chemists came up with a superhero equation, the gas equation. It helps us calculate how volume changes when both pressure and temperature vary at the same time. Think of it as a combined control system for gases in every real life situation. Let's build this step by step. From Boyle's law, we know that volume is inversely proportional to pressure at constant temperature. Mathematically, V is proportional to 1 over P. From Charles' law, volume is directly proportional to absolute temperature at constant pressure, or V is proportional to T. Combine both relationships and you get V is proportional to T divided by P, or simply V equals K times T over P, where K is a constant. Rearranging gives us the famous form PV divided by T equals a constant. And there you have it, the gas equation, born from the marriage of Boyle's and Charles's laws. Now, how do we apply this equation? Consider a gas under two different sets of conditions. Initially, it has pressure P1, volume V1, and temperature T1. Later, it changes to pressure P2, volume V2, and temperature T2. According to the gas equation, P₁V₁ over T1 equals P₂V₂ over T2. This is our working formula. It's powerful because it can reduce back to Boyle's law or Charles's law if either pressure or temperature remains constant. And of course, don't forget, temperatures must be in Kelvin. If you plug in Celsius, the gas will not forgive you. Equations are neat, but why does this really happen? Kinetic theory explains it beautifully. Take Boyle's law. At constant temperature, if you increase the volume of a container, gas molecules travel longer distances before striking the walls, so collisions decrease and pressure drops. If you halve the volume, collisions double, and so does the pressure. Now, Charles's law. When you increase temperature, the kinetic energy of molecules rises, double the absolute temperature, and molecules move twice as energetically. They hit the walls harder and more frequently, increasing pressure or volume. So, these gas laws are nothing but the visible outcomes of invisible molecular collisions. Here's a practical challenge. Gas volumes keep changing with pressure and temperature. How do scientists compare results from different labs? Simple, they agreed on a reference condition called standard temperature and pressure. At S.T.P, the temperature is 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atmosphere, which equals 760 millimeters of mercury. Whenever gas volumes are reported, they are often converted to S.T.P so comparisons become fair. It's like everyone using the same time zone when arranging an international meeting. Let's solve a numerical example. A gas occupies 700 milliliters at S.T.P. That means pressure P1 equals 760 millimeters of mercury, volume V1 equals 700 milliliters, and temperature T1 equals 273 Kelvin. Later, the gas is at a pressure of 400 millimeters of mercury and a temperature of 15 degrees Celsius or 288 Kelvin. What's the new volume? Using the gas equation, P₁V₁ over T1 equals P₂V₂ over T2. Substituting 760 times 700 divided by 273 equals 400 times. V2 divided by 288. Solve for V2 and you get approximately 1403 milliliters. So the gas almost doubles in volume when pressure falls and temperature rises. Isn't that a perfect demonstration of how gases juggle multiple factors together? Now let's bring this back to the real world. The gas equation is used in calculating gas volumes in chemical reactions, especially when conditions are not standard. Industries rely on it to safely fill and transport compressed gas cylinders. Balloons change their volume as they rise higher in the atmosphere, and pilots must account for this expansion. And most importantly, this gas equation forms the foundation of the ideal gas law, PV equals nRT, which is the heart of physical chemistry. So, to wrap things up, Boyle told us how gases respond to pressure, Charles taught us how they react to temperature, and the gas equation unites both stories into one beautiful relationship. Remember, PV over T is constant for a fixed amount of gas. From puffed up chip packets to industrial gas cylinders, this law is silently at work everywhere. I hope this session helped you see gases not as invisible emptiness, but as energetic dancers obeying strict mathematical choreography. See you next time for more chemistry adventures.